Morning, afternoon, or evening. So this will be our first day with magnetic fields, uh, day 13 in the fields unit. Okay, so let me just set up here. Get Blackboard open and also maybe throw the preview back on here. For some reason I got to turn that on every time. Okay, so what we're going to look at today on day 13 is basically magnetism, and we're going to look at a couple of things today with magnetism, just the domain theory of magnetism and how it works, and then look at magnetic induction and magnetic fields. So those are the things that we're going to look at today. Okay, so let's set it up here, day 13. And we're looking at today, it's still in unit 3, the fields unit. And we're looking at basically magnetic fields. And we're going to be looking for domain theory of magnetism. Okay, we're going to be looking at magnetic induction as well. And basically, we'll probably look at some magnetic fields in terms of diagrams. And then we'll talk about some of the other things that we're going to be looking at as well is, the right-hand rules that apply to flowing current and magnetic fields that they create, things like that. And that'll probably be it for, that'll be it for the fields unit. A few more days of that, and then we'll have our second hand in. And then we'll be done our fields unit here in May. And then end of May, we'll get into our last unit, modern physics, which is fairly short. Again, our goal here in physics online anyway is to be done in early June so that we have a week or so extra in there for ourselves if we need to get ready for the final, or if people are in the need of, some people might be farther behind than others and might need that catch-up time. So I like to finish in early June rather than later in June. And that should be possible for us this year. Okay, so let's talk about the domain theory of magnetism. Let's use a different color here. So first thing that the domain theory of magnetism states to us is that the materials that have the ability to produce a magnetic field are called ferromagnetic materials. That's a term that they use. So ferromagnetic, oops, I guess, I don't know if it's a slash word or not. I think it is. Materials are ones that have the ability to become magnetic. Okay, so sometimes you have to induce the magnetic field on them. The one that material that's naturally this way is magnetite. Okay, so magnetite, which used to call in the old days lodestone, is the only natural occurring magnetic material. Okay, so magnetite is like that. Okay, and that's a couple of facts in there. And the first thing, according to the domain theory of magnetism, ferromagnetic materials have large amounts of atoms in them, and they kind of act like mini magnets. Okay, and because of their poles that they have. Okay, they have like little poles, magnetic poles on them, and they call these domains. Okay, so that's where the domain theory comes in. So the basis of the domain theory. So in domain theory, let's spell that right. It's thought that ferromagnetic materials have large amounts of polar or mini poled, we'll say, or large, well, actually they're atoms. Atoms, large amounts of atoms that act as mini poled magnets called domains. These are called domains, we'll put in brackets. And it basically, the reason that they act like the little mini magnets has to do with their properties, their chemical properties, or their alignment, whether they're poled atoms or something in that way, the way the electrons are rotating in the orbits and things like that is what the theory thinks, but we don't need to go that deep into it. And in a material that has magnetic properties, these domains basically have aligned in the same direction together. Okay, so what they say is that in a magnetic material, domains become aligned in the same direction. Giving the material a magnetic property, or giving it the material its magnetic property. Oops. Oh boy. Let me move that up. Because I know that the preview is a little bit different. For me now, all I see is myself. They don't show me the preview of what I'm recording on screen anymore for some reason. When they updated Screencastify, said it might be an update or some setting that I have to do, but I haven't figured out yet. Okay, so that's basically the theory of if materials have no magnetic properties, they say that these domains are all scattered around. Okay, and that's basically the theory. And we'll draw a little picture. If a material is ferromagnetic, but shows no magnetic field, domains are believed to be scattered. In the material. Okay, so if we draw this out, ferromagnetic materials are believed to have these little domains, the atoms with special properties that allow them to act like magnetic, little tiny magnets. So if we had, just draw it underneath here, we'll move this up a little more. Okay, so if we say we got a bar here, make it, oops, let's get my marker out here. There we go. So let's draw two materials here. Okay, and let's say that this one here on top, this one's going to be, they usually use a little arrow, which represents a domain. Okay, and one part will be the North Pole, one part will be the South Pole of the domain. Okay, and if you have in here the domains just kind of being scattered all over the place, pointing in various directions, they kind of cancel each other out. So this would be a ferromagnetic material. Okay, with scattered domains. And we see no limited magnetic properties of the material. Okay, they're kind of canceling each other out. Okay. This is the non-alignment. Of the domains. Okay, if you put it in a magnetic field for a while, like the Earth's magnetic field, or a strong electrical current or something like that, which will produce or induce a magnetic field, what will happen is these domains will, if they kind of get aligned up like this, and they all point in the same direction, okay, they're all kind of lined up. And this is a piece of magnetic material then. The domains have lined up, and then they would create a magnetic field around the bar. So this is a piece of, this is ferromagnetic material. With aligned domains. As a result, we will see magnetic properties. In the material, or for the material. Okay, so we have aligned domains there. Okay. And then you would see a magnetic field being produced as well. Now, if you have a non-ferromagnetic material, there's not even domains in it, or very, very, very few atoms act like domains. So if you have a non-ferromagnetic material, let's throw one more in here. That's why it never becomes magnetic, even though you try to induce it. So if we draw one more here. Okay, if this is a non-ferromagnetic material, we may see very few domains in there. So, oops, wrong one there. Okay, if this is non-ferromagnetic or not ferromagnetic, we could just do that. No, very few domains are in the material. Very few atoms act as domains. So we can just draw some lines for atoms or whatever, but you might have on all these particles, you might have one or two domains. That's it, not very many at all. Okay, maybe none particularly at all, depending on what type of material it is, right? So if it's non-ferromagnetic, no domains or very, very few domains exist. And then therefore they can't become aligned and they can't have magnetic properties. So there's no magnetic properties. And no properties, or sorry, magnetic properties, pardon me. And no ability to induce a magnetic field. Or induce alignment either. Oh, I spelled that wrong. Whoop, Razor, where are you? There you are. Okay, so you can't really align them either because there's no domains in there. Okay, now in the other piece here, this one up here, you could induce a magnetic field if you put it in another magnetic field and then all these domains would align. See, there is a possibility to align any ferromagnetic material. Something is non-ferromagnetic though, or not ferromagnetic at all. It doesn't have enough domain particles acting like domains in them. And so that's the theory of domain theory, the basis of it. And I believe chemically they believe that the magnetic properties are really having to do with the many domains are caused by a particular phenomenon with the atoms, rotational electrons, and things like this, if I remember correctly. But at a high school level, we really are only interested in the domain in itself becoming aligned and how that works to induce magnetic fields in materials that are ferromagnetic. Okay, so magnetic fields and flux is what we'll look at next. So when we've all seen magnetic fields, okay, and maybe you haven't heard the word flux before, or maybe you have, depending on and what it means, and we'll talk about what magnetic flux is, and we'll draw the typical magnetic field, okay, around a magnet, and then probably what we're going to do after that is we'll probably get into some of the right-hand rule stuff that we deal with. I'll pull out some not today, but maybe tomorrow I'll bring in some wires and some compasses and things like that to demonstrate. And I'll have to do that, set my camera up here, and we'll have to just to demonstrate, how flowing electricity causes magnetic fields as it flows. So we'll start with that today. So let's flip our page here, and let's go into magnetic field and flux. Okay, so that's our next little topic here. Okay, so we're going to talk about magnetic fields. And flux. Okay. So a magnetic field is a space around the magnet where a magnetic force can be experienced. Okay. Okay. Another thing is, keep in mind that magnetic force can also be produced around currents. Electricity. Okay, so if you have flowing electricity, you have magnetic field as well. But we'll just do the basics of magnetic field. So let's draw a little bar magnet here. And we know this from, we probably did this in our early science years a little bit. Okay, so if we kind of take our tool out again here, get our shape, let's make this one kind of in the middle here so we have space to draw around it. This is our bar magnet type. So what you'll have is around this, you will see if we have each of the poles. So let's put the poles down here. Okay, our north pole here and our south pole here will go. So what happens with a magnetic field is the north pole, the magnetic field lines come out of the north pole and flow into the south pole. Okay, so and in a bar magnet, the magnetic field lines will be very close together inside the material. So we'll use a dotted line there. Okay, and so let's go run right down the center here. Let's use a different color, I guess. So we can put we'll go medium line on this. So okay, and we're going to put, I'm going to try to draw in here maybe 5 really close together dotted lines here. 3, 4. I wanted one more in there maybe. Yeah. Actually, if I use a dot line tool, it might be better. Let me do that. That might look a little better. Okay, I'm just going to see if I can draw this a little bit better. Okay, don't worry if you already start drawing it. I'm still going to draw the same thing. Okay, let's put the north-south poles back in there. But I'm going to use maybe a straight line tool. Not that one, but let's say this line here. And we will make it medium size and throw some dots to it and make it our green color. Okay, so one right down the center. Yeah, that's nice. then I'll get some nice straight lines here. Okay, and then we'll go one right beside it, two on the top here, evenly spaced. There. And then we'll go two on the bottom here. So nice 5 lines in there. Could even throw another one down, but 5 will be nice. Okay, so these represent inside the magnet. We have a very, very strong magnetic field lines. They're very close together there. They're inside, they're dotted usually like that. Then outside, we'll draw our curved ones that we see. So the center one is going to come out here, and we'll get into green here. So we have to go into hand drawing here. And we will make it a solid medium-sized line. Okay, so that first one kind of comes out like this. Okay, then this one here, we're going to kind of come out. We're going to bend it around nicely, kind of do a nice even loop like this, and get back into it here in the South Pole. Oh, that one wasn't there. Let's kind of make it better there. And in there we go. Not the first one, second one. That, my drawing skills are legendary bad. Let's get that a little wider there. Okay, so come around and into that second line there. Okay, and we have coming out like this. This arrows represent the force direction on that magnetic field line. Okay, then we'll come in here. This one here has a tighter loop. These are farther apart than in here. Okay, going in there. We'll label this up good. Okay, same idea here. This one can come out and have a kind of a symmetrical kind of look to it. Okay, we have, right, and then we've got this one is a tighter loop inside here. Kind of a symmetrical look to it as well. If you can do that. Okay, you'll notice that the magnetic field lines are closer together here than they are out here. Okay, so if we label this up, the green is the magnetic field line. Okay, the dotted ones are also magnetic field inside the magnet. Okay, and you can also, if you wanted, you could kind of throw some more out here like this. Right, if you wanted to throw a few more in there like that, whatever, make a great big magnetic field. So anyways, you can see that the magnetic field lines are closer together here and than they are at the edges of the magnetic ends, so that you'll have a stronger one. And what that's called is the magnetic flux, is the number of magnetic field lines per unit of area. Okay, the more lines you cross per unit of area, the larger the magnetic flux, which would be the magnetic field. So that's what we call magnetic flux. We'll type that underneath here. You'll notice that they're really close here, really close together here, but farther apart on the edges of the magnet. So magnetic flux, get back into our green color, keep it the same today. And when we talk about magnetic flux, okay, this is the number of magnetic field lines per unit of area in a magnetic field. Okay, note the edges have higher magnetic flux than, or let's say the north and south pole. As well as the interior. Of the magnet have high magnetic flux. And the edges of the magnet are lower. Okay, the more field lines across, the larger the magnetic field flux. Okay, in that area, okay? And that's the magnetic force that's in there. So that's a typical bar magnet that we have. We'll look at some other magnetic fields as we go along. Okay, let's take a look at our time here, see what we're doing here. Okay, that's about 32 minutes, so we'll go a little bit longer on one. We'll do one quick topic here. Let's go with, we should probably, before I do that, I know what we can finish up with. Just some reminder of magnetic properties. Okay, so just a couple reminders of the magnetic properties. For magnets, okay, we have like poles on magnets, okay, create repulsion, force of repulsion. Okay, and opposite magnetic poles create the force of attraction. It's similar to our electrostatic stuff. Okay, so if you were having looking at a bar magnet like this, where magnetic force is coming out of a north pole and going into a south pole, that's why they attract. So if you have, for example, just draw a little diagram here. Okay, if you have a north pole and a south pole close together, like that, the type of magnetic field that you get. So you notice that it comes out here and goes in there. So it's going to go from north to south. So we are going to see a magnetic flux, or the field lines. And I'm going to just draw it with an arrow because that'll help us a little bit. And let's make it medium size. It's going to go like this. That should have been a straight line there. Okay, it's coming out there, going in there. So we see magnetic field lines and we see attraction. Okay, it's going to pull the north and south together. North is going to come towards the south there. Okay, if we see two two norths together or two souths together, it'd be just do two norths. Okay, we have a north here. We have a north here. So this time we're going to see magnetic field lines coming out from both the north like this. And then we're going to see that repulsion bend thing. So then this one's going to repel on that one. Let's get it black here. So it's kind of going to go like this. And we see repulsion. Okay, we have magnetic field lines still in there. But we're seeing repulsion. Okay, we see that they're kind of hitting each other and then bending around and giving us that repulsion type force. And our magnetic force can be very, very high as well. We often think of it as a weak force, but it can be very, very high. Okay, so we still want to talk about magnetic force around current carrying conductors and things like that and the right-hand rule. But we've got into about 38 minutes here, so I think that's a good spot to stop here. We don't have to hurry now. We just got part of this unit left here in mid-May, and we'll be done fairly quickly. And then what's left after that is just modern physics, which is a couple-week unit, 2 to 3 week unit, depending how deep we go into some of the things. And that'll be it for us in physics. And like I said, we're trying to shoot for getting done in the second week of June or something like that. Okay, so that'll be it for today, and we'll see you guys tomorrow where we'll talk about current carrying wires and magnetic fields.